Unmute. Hello, everyone. This is Rich Ozer. I'm at the Chabot Space and Science Center tonight, and I'm sitting in front of our 36-inch research telescope, who's affectionately named Nellie. And I thought it would be an appropriate venue for this evening's talk. Tonight, I'm going to speak about astrophotography. The title of the talk is Astrophotography 101. And that means we're not taking a really deep dive into the topic. What we're doing is giving you an overview of the hobby of astrophotography, what technologies are popular, what you can do with some of the equipment you might find at home. And if you are really interested in this technology and interested in the hobby, maybe to pick one of the areas that I'm going to talk about as a goal for yourself, and to understand a little bit more about what's involved, what kind of equipment you'll need, and also, quite importantly, what it would cost to get into it. And we'll talk more about that aspect of it later as well. I'm also here with Gerald McKeegan, who is keeping me company. He's busy trying to crash his spacecraft into the International Space Station while I give this talk. So if you hear a loud bang or curse coming from my left-hand side here, you'll know what that's all about. Anyhow, it's a nice night up here. I'm glad to be up here, and I hope you're all doing well and staying healthy, and we hope to be able to see you in person sometime soon. Anyhow, I'm going to get started. This is mostly a PowerPoint presentation, although we do have some show and tell along with it. It's kind of hard to talk about this topic over a Facebook Live or a Zoom presentation as a lab or as a hands-on, because there's limitations to the camera on the laptop, and there's limitations to the media. So I'll try to make this as entertaining as possible. And just so you know, there's not going to be any really hard math or really dense slides or anything like that. It really is meant to be a relaxed overview of astrophotography. I'm going to go ahead and share my screen now with the PowerPoint presentation. Bear with me here. All right. There we are. Okay. So as I said, I'm Rich Ozer. I'm president of the East Bay Astronomical Society and a longtime volunteer here at Chabot. I've been very interested in astrophotography for the last decade or so. Before that, I was almost exclusively a visual amateur astronomer. And I reached the point where I had a choice. And that choice was to either get a larger, much larger aperture telescope and haul that around, or to get into astrophotography and try to photograph objects that were increasingly difficult to see, either because of light pollution or because the increasing age of my eyes. And I decided to go for astrophotography. And part of that was because I work with technology in my day job. I'm very comfortable with software and with electronics. And I just figured that was the way to go. And the opportunity came up some years ago when a friend of mine was selling some equipment, and I went ahead and purchased it, and there was really no going back for me. So I hope that you'll appreciate some of the steps I took in this journey, and I hope you'll find some aspect of this that speaks to you and to what you might want to do. Advance the slide. Okay, so none of this would be possible. It certainly wouldn't be possible for me if it wasn't for the digital camera. Before the digital camera, astrophotography involved hooking up a telescope to a camera, sitting in front of the telescope all night long with a reticle eyepiece, and taking very, very long exposures while manually keeping a guide star in the center of the crosshairs. And you had to have a lot of stamina to stay awake You had to be able to stay still, and you had to be completely immune to the cold, I suppose. And you had to be immune to incredible boredom as well, because it was a fairly long and arduous process to get a good astro image. The result, of course, was stored on film or on glass plates, and that's how astrophotography was done for decades and decades and decades. But once digital photography started to become approachable to the general public, and we started to get consumer devices that were taking advantage of this technology, it was a real game changer. It meant that instead of taking single exposures that were hours long, we were able to take many short exposures, not worry if the camera shook or if something, flashed in the field of view. Because of the power of software and because of the power of the electronics that are associated with these cameras, it became a lot of fun to work with the equipment and work with the guiding equipment and to work with the capture software on laptops or computers. And the two types of cameras that were generally available and have been available for many years are called CCD cameras. CCD stands for Charged Coupled Device, and CMOS cameras, complementary metal oxide semiconductors. The camera that's in your cell phone and the camera that is in a typical point and shoot or even DSLR camera is a CMOS camera. The type of camera that advanced astrophotographers have traditionally used are CCD cameras. Now, the difference is a little bit subtle. In the graphic that you see on this slide, you can see that on the left-hand side, there's a matrix of squares. And on the right-hand side, there's a matrix of squares, but with symbols of electronics inside of them. So let's talk about the CCD first. What's going on with a CCD sensor is that light comes into the camera, and the nature of light is that it can be described as either a wave or as photons. For our purposes, it makes more sense to describe light as photons. And you could think of each of those little squares or pixels as individual wells that are capturing those photons. And so when light hits the sensor, the photons enter the various wells. They're brought to focus by the lens in front of the camera. And what happens is a charge builds up in each of those little squares. And that charge represents the amount of light that has been captured by that pixel. So some pixels will have a big charge and some pixels will have a little charge. The ones with the bigger charge are going to be brighter. So the game then becomes how to get that information off of the chip and into a file that can then be processed by your software and eventually printed out or displayed on Facebook or wherever you like to display your photos. So the CCD shunts all of that information off to the side and then converts it to a digital image. The CMOS sensor actually has smart pixels in a sense. Each pixel has the electronics to convert the photons to the electron signal, and then it's able to read directly from the pixel what the value of the individual light bucket is. So it seems like a subtle difference, but the reality is that CMOS sensors are much cheaper to manufacture. And they're also noisier. There's a lot more electronics going on. There are a lot more amplifiers in there. So they tend to be a little bit fuzzier in the result of the raw image. But the CMOS technology is what's going to be driving the hobby. More and more cameras now are CMOS cameras, and there are fewer and fewer companies manufacturing CCDs. The thing to realize is that astrophotographers have always been at the back end of this market, right? Nobody is building cameras to satisfy, or building sensors to satisfy the astrophotography market. CCDs were built for the biomedical market. CMOS sensors were built for cell phones, and clever people have adopted those technologies to incorporate them into astrophotography cameras. So whatever the industry is doing, we have to kind of live with, and then we'll purchase the products that do the best job given the technology that's available. The other main variable about any type of camera for astrophotography is the speed of the lens. And you've probably heard of fast lenses versus slow lenses. Now, really the best way to think about a fast lens is that it's one that allows you to capture an image in low light conditions. So you want to have what's called a fast focal ratio, and you want to also have as big an aperture as possible. Now, of course, when you're looking at a cell phone, probably can't see this here, but you all know what a cell phone looks like. The camera lens on the back of a cell phone is tiny. It's like at most 1/4 of an inch wide, and it's probably a little bit smaller than that. But they're incredibly fast. They have a very, very short focal length. It's almost like having a wide angle or fisheye lens on the back of the camera. And that's why they're able to do as good a job as they do under low light conditions. And that's what makes them possibly useful for astrophotography if you don't feel like getting anything more advanced. And the first part of my talk, probably the first 20 minutes or so, is going to be about what the variables are for using a cell phone camera to capture some astronomical images. I'm going to probably just gloss over this slide. This pretty much just shows you how a point of light indicated by the gold arrow passes through the lens on the camera and then comes to a focus at the very right here. So one point of light comes to a focus here on a pinpoint. And you can see that focus is critical, because if you don't focus well, it means that a pinpoint of light from the source is going to be spread out over multiple pixels rather than a single pixel, and you'll end up with fuzzy stars. So focus is one of the important variables, and I'll get into that in a little bit. All right, so I've identified 4 levels of complexity of astrophotography. The first level is just cell phone night photography, and I would consider astrophotography to be just one part of night photography in general. Level 2 is using a DSLR, a single lens reflex digital camera, with short exposures, no special guiding, but maybe with motorized tracking. Level 3 is shooting video with a DSLR, also unguided, also with motorized tracking. And level 4 is using a CCD or CMOS dedicated astrophotography camera or a dedicated DSLR using shooting long exposures with the telescope mount guided and with motorized tracking. And that's where the most advanced and ultimately most expensive equipment comes in. The general rule is that visual astronomy is all about the telescope. Astrophotography is all about the mount. And that's a rule that pretty much holds up across the board, unless, of course, we're talking about cell phone photography. All right, well, let's talk about the different types of cameras and what their positives and negatives are. For a cell phone, well, we have poor control over exposure and in-camera processing. Most cell phones have very limited manual control. And in almost all cases, you need third-party applications to capture low-light images. Now, there's some exceptions to that. I'll go into that in a bit. For the DSLR, you have very fine control over exposure and in-camera processing. You could swap the lenses. You have all kinds of adapters you can work with. They have fast download. The image gets stored onto the camera chip or can be sent over a USB cable to a laptop very rapidly. And with a DSLR, you can interface the camera with a computer. Some of you have done that. Many of you who have a DSLR probably have tried it to some degree, but there's some very advanced software available for DSLR cameras to allow you to control and acquire images directly onto a laptop. For CCD and CMOS cameras, they are extremely sensitive by an order of magnitude over DSLRs and cell phones. They are often cooled, meaning that there's a refrigeration system inside the camera. There's a type of refrigerator for electronics called a Peltier cooler that actually transfers heat using a solid state technology. And you can bring the temperature of the sensor down to 10 or 20 degrees below 0 centigrade. And these cameras are, of course, they're built for the application. They're built to do this high resolution photography and over a large field, and they're meant to gather large amounts of data without the interference of the rest of the electronics. They don't have any special filters in front of it for daytime photography. Like your DSLRs, for instance, have an infrared filter when you buy the camera, and that filter gets in the way of certain types of astrophotography. Some people choose to have that actually removed before they use that camera in an astrophotography application. But a CCD, it's just a raw sensor with mounting equipment on it, and you stick it in a telescope. So let's talk a little bit more about cell phone astrophotography. Yeah, that looks pretty much like my pile of cell phones at home. One of the things you can do is grab an old cell phone to try this with. If you don't feel like doing it with your new phone, you can grab one from a few years back and try your hand at it and see what you can come up with. You certainly don't need the phone features to do this. You just need the camera features and the Wi-Fi features, perhaps. This is what I tell people. I spent 10 years as a photographer for a newspaper, and composition was everything. And to get a good photo, you've got to think about what it's going to look like after you take it and get the subject framed in such a way that it's going to be interesting to look at. So for composition, I say use the grid. Now, if you don't know what I'm talking about, most cell phone cameras actually have a setting that allow you to turn on a 3x3 grid that you can see on the screen of your camera. And the general rule of using that grid is put the interesting parts of your subject wherever the lines intersect. So you can see in this picture that the head of the bee is right there in the cross between two of the lines, right there. And you're not really just like centering the whole thing. You don't have like an object just in the center of the screen with negative space around it. But again, you want to embrace negative space and maybe have it off to one side and don't have the photo too busy, but also don't just have it right in the center or the subject right in the center. Also learn how to manually focus your shots. One of the problems with night photography is focus, because if you rely on autofocus, the camera is rarely going to get it right at night, because it's going to find something that it considers close and bright, and it's going to try to focus on that. So manual focus on a cell phone for night photography can be very important, and only some cameras allow you to override the manual focus. And that's one of the reasons you have to sometimes download and install third-party applications to get around that. All right, rule number 1, turn off the flash, especially around windows. One of the big mistakes people make whenever they're using any kind of camera is just assume that the flash is going to make their photos come out correctly. I find that it's mostly the other way around. And what you want to do is turn up the sensitivity of your camera, try to take an image without the artificial light coming from the camera, and try to capture the light as it is naturally in the environment. And you can see that in this photo. This is an absolutely horrible photo, and you are seeing mostly the reflection from the flash through a window while we're trying to photograph the buildings beyond. This might actually be a really nice photo if the flash wasn't on. Avoid the zoom feature on your cell phone. And hint, it's not a real zoom. What the zoom on your cell phone camera is doing, unlike the zoom on a DSLR camera, is it's not actually moving any parts. It's not moving the sensor or changing the distance of the lens from the sensor. All it's doing is blowing up the resulting image. It's a digital zoom, not a real zoom. So the result is that you end up with a kind of a blurry image when you zoom in. I can't even really tell what this is a picture of. I am told it is 3 pigeons. I can't swear that that's the case, but it kind of gets the idea across that that zoom while you're taking the shot from the cell phone is not always the best idea. Your cell phone is not the Hubble Space Telescope. This is a typical moonshot from a cell phone. It looks like somebody has taken a pencil and punched it through a piece of paper and held it against the phone. You got a little dot surrounded by black space, and that's about what the size of the moon would be if you pointed your cell phone at it. Now, it's funny to look at this and think that it's the moon, but this photo actually has a couple of redeeming features. In fact, it has exactly 2 redeeming features. The first is that the background here is nice and black. It is real black. And the subject, which is the moon sitting there right in the center, is very white. So it's got good contrast. The other thing that's great about this photo is that they managed to pull it off without having a bunch of noise, and also it's in focus. So actually that's 3 features: no noise, good contrast, good focus. And this, even though you would not be turning this into any photography contest, is something that when you play with your phone, you should be able to achieve. So go out on a full moon and see if you can do this. If you can't get your particular cell phone to take this image, then probably that cell phone is not going to be a very good phone for doing anything more advanced in the way of night photography or astrophotography. And I'm not saying that because, oh, there's something wrong with you, you can't take this photo. Every cell phone is different. Some cell phones simply can't do this right. Others have better design software and cameras and are much more capable of pulling off this type of thing. So instead of spending a lot of time at first trying to do hard things with astrophotography and a cell phone, make sure you've got the daytime stuff down, right? What can you do with the sun and clouds? Can you get interesting shots of atmospheric phenomena? So this is a shot that shows a sundog, right? You got the sun on the right-hand side of the image, and you've got the refraction from ice crystals off to the left. Here's another, he's a much better one. This one was taken by my friend Marnie Berenson. She's with the Mount Diablo Astronomical Society. She shot this from her house in Walnut Creek, it looks like. And again, you've got the sun in the center, and you've got the ice crystal refraction on both sides of the sun. Now, she's doing a trick here also. With a cell phone in particular, a bright sun has the potential for washing out the entire image. So by positioning herself behind that tree, she's able to reduce the amount of light from the sun and get more contrast for the rainbow effect off to the left and off to the right. Practice on sunsets and reflection. Now, there's a few of us, at least one of them is listening to this talk, who go out periodically to Alameda Point and try to get cool looking photographs of San Francisco across the water. This is my favorite one that I've been able to do so far. And this is using a Google Pixel 2 cell phone. And it is about 15 minutes after the sun actually set. And it's enhanced a bit using the slider controls on the camera after the fact to increase.
Here's what I found on the web.
Excuse me.
Here's a matching video.
I got my phone started talking to me because it heard me mention its name. I said the word Google and it woke up my phone. So just in case you think that they're not listening to you, there's the proof. So anyway, that image was taken about 10-15 minutes after sunset, enhanced after the fact. But it was in order to practice getting high contrast images after dark, and to try to also pick out the pinpoints from the lights from the building. And I think that was well achieved. This is my refrigerator magnet photograph. So I think that's what I want to turn this into. Here's another one by Bill Drelling later in the season. And again, capturing the sunset, high contrast, getting good blacks, getting a nice view of the sun, getting some nice colors. So these are the types of things you've got to master first, in my opinion. But part of using a cell phone for any kind of astrophotography is to figure out how to get it attached to a telescope, because you saw that taking a photograph of the moon directly is not going to be a very appealing photograph. There's some other types of astrophotography that you can do with a cell phone, which I'll talk about in a bit. But most of you are going to be interested in hooking it up to a telescope using some type of apparatus. So I found a good video from our friends over at Orion Telescopes in Cupertino. And this is not to necessarily endorse this product over any other, but it gives you a good overview of what you need to think about when you hook up a cell phone to a telescope. And I'm going to play this video, and let's see if this works here. Hi. All right, well, I'm told that the video isn't coming through on that, which is unfortunate. So what I'm going to do instead is describe a little bit what he's doing. So the idea is to use what's called a cell phone to telescope adapter. And it is a device that hooks onto either the eyepiece or to some other part of the telescope, and allows you to align the lens of the cell phone with the ocular or the eyepiece that's attached to the telescope. And once you've got that aligned, you can use the focus on the telescope and take a shot of whatever it is that you've got the telescope pointed at. You have to practice with this. So what a lot of people will do is first put the eyepiece in the telescope without the adapter, get it aimed at whatever you want to shoot. Let's say it's the moon or something else. And then attach the cell phone adapter to the eyepiece, get the lens aligned with the eyepiece, and then start shooting. As far as the exposure goes, auto exposure often works. Again, if you have manual control over the camera software, either using what's built in or with a third-party product, that might work a little bit better. But the idea is to have some device that holds the phone steady. Orion started selling these products when they realized that people were coming to their star parties and spending all their time holding their cell phones up to the eyepiece trying to take a photograph. And what happens is your hands are shaking a little bit, and people assume sometimes that the lens is in the middle of the camera, so that it's offset, and mine's off to the right. And so first I got to figure out where on the eyepiece I have to hold the camera, and then if you're holding it too close, it will vignette. If you're holding it too far, you get a picture of the eyepiece. So it's not that easy just to hold a cell phone up to a telescope eyepiece. So these holders do a pretty good job aligning and steadying the cell phone. And if you want to take photos of the moon through a telescope, it's a required tool. There's really no way around it. And I would suggest searching for cell phone telescope adapter. And if you Google that, you'll find a zillion products. Orion has some good ones. There's several other companies that make good ones as well. They're not very expensive either. And yes, it's possible to get an excellent shot this way. Alan Roche took this through Leia. It's cell phone image. And there's, that's as nice as anything you can get through any other means. So what about deep sky photography through a cell phone? Now, that's hard. That's really hard to do. You need a good way to steady the phone. You need manual control over the ISO, and the ISO on a camera, on a CMOS camera, is the sensitivity to light. It's basically how much is it going to amplify the light. It's good to have manual focus. You want to store the image in what's called RAW format. Usually images that are stored on your phone are JPEGs, but there's another format called RAW format, which has all of the data from the sensor. And it allows you to use software such as Photoshop Elements and other products to manipulate the image in a more advanced way. And you want to be able to determine the exposure time and be able to take long exposure images. You generally want to turn off HDR. HDR is a high definition technology that's built into our cell phones, where it's actually taking 3 images in rapid succession when you shoot the camera, and then it combines them in such a way to give you darker darks and brighter lights and higher contrast under difficult conditions. You generally want to turn that off when you're doing astrophotography on your cell phone. You want to set the aspect ratio to maximize the use of the sensor. In most cell phones, that's 4:3. And then you want to be able to trigger the cell phone with the timer. So you want to have the cell phone being held steady through some mechanism, and then you want to press the button to shoot and then step away, and then it will start taking its shot a few seconds later. An easy way to build a tripod for a cell phone is to take a cup. Imagine this is a plastic cup. I don't have one with me. And you could cut slots diagonally on each side and then slide the cell phone in, and it will actually act as a cup tripod for your phone, pointed at roughly 30 or 40 degrees. And you can aim it towards the southern hemisphere with the expectation of trying to take a Milky Way shot. In my opinion, it's really the wrong tool for the job. I think that's really stretching it. Some people like to play with it just because they say they can. And so it's a fun challenge, but it's much harder to do than using a regular DSLR camera or other set of tools. But if you're interested in that, I'd like to refer you to a website. and that's www.MatthewRiley Photography. That's MatthewReilly photography.com. And he has a blog and an instructional video on how to do astrophotography with a cell phone. And you can see that these images here, he has both a monochrome and a enhanced raw image and an edited raw image of an individual standing in front of the Milky Way taken with a cell phone. Now, his particular cell phone is well suited to that because it will allow up to a 30-second image. You can put the camera on manual control, start the photo, walk away for 30 seconds, and it will gather that much data. Now, I have a Google Pixel. I don't want to say that again. It's going to start talking to me. I have a Pixel 2, and it only allows me to take a 2-second image. That's the maximum that the hardware supports. So I would not be able to do this with my cell phone, and I'm willing to bet that most of the cell phones out there cannot do 30-second images. I'm not sure about the iPhone, and somebody's going to have to tell me what the iPhone can do. Anyhow, I'll post the this website name to onto the comments list of the Astrophotography 101 post on the Facebook page after I'm done, if anybody is interested. All right, well, moving on to the next level, we'll talk about fast, motorized, unguided astrophotos using a DSLR camera. And that's suitable for bright targets, either during the day or at night. It involves just the camera or a camera plus the telescope. And this is a portable and relatively inexpensive solution, especially if you already own a DSLR or a camera that allows you to have changeable lenses. You may or may not own a telescope. You may just want to use a zoom lens for your camera. And there are certain tools you can get for your DSLR or for your one shot that make it work kind of like a telescope. And these are two products that I'm particularly fond of. One is the Vixen POLARIE, which is the white one here at the bottom. And the other is the Ioptron Sky Tracker. And both of these sit on top of a tripod and turn the camera mount into a pseudo equatorial mount. So the camera will actually be aligned with the pole star, and you can then take semi-guided, really just timed images up to 30 seconds long or sometimes even a minute long, just having a camera attached to one of these gadgets. And the results can be stunning. Now, these gadgets are anywhere from $250 to $350, and you need a good solid tripod to put them on. You can see that on the upper left photo, how it's mounted onto what looks like a Manfrotto tripod. And the result can be something like this. This is a DSLR shot, and it's a stack of 10 one-minute shots of a globular cluster done with a Vixen POLARIE. John Hoey, my friend from San Diego, took this shot in Monterey County several years back. And he kind of mastered this technology for a while and was churning out some pretty good images. This is another one he did. This is just using a 250 millimeter lens, the Vixen POLARIE again, 10 one-minute long shots. And he got an image. It's hard to see, I'm sure, in your screen, but inside this circle here, he was able to identify Proxima Centauri. And that's pretty good with for a $300 mount and a standard DSLR camera. You could also take deep sky objects like nebula. And this is 32-minute exposures. And you could look at the stars on there and you really don't see any elongation. So it does a pretty good job. If you get the thing polar aligned well, then the tracking is remarkably good. Now, the next thing you can do with your DSLR is attach it to a telescope and put it on a simple mount, either a tripod or an inexpensive motorized mount. And I'm going to grab a DSLR here. I'm going to stop the sharing for a moment. So this is a standard DSLR camera. This is a Canon EOS T1i. Nice thing about these cameras, of course, is that the lenses are removable. So if I remove the lens, I could replace it with something called a T adapter. And a T adapter is just a piece of tubing with a bayonet mount attached to it that allows you to insert the camera into a telescope. Now, I could go ahead and put it in Ellie right here. And there we go. I've got, I got the DSLR attached to a non-portable telescope. This is not what I'm usually doing. So what I have this set up for is for lunar photography and for solar eclipse photography. And I have this telescope that I like to use. I bought this several years ago, and it's a William Optics Zenith Star telescope, and it's just about the right focal length for shooting the moon and the sun without needing to magnify the image between the telescope and the camera. And again, I could just fit the camera into the telescope like so and shoot away. If you're shooting the moon, you really don't need any special mount. The exposure times are short. You could usually do something at, a 200th of a second, set the ISO to, 200 or 400. If you're doing solar eclipse photography, there's some special techniques, which if I have time, I'll talk to you about in a bit. If you want to do deep sky photography, then you need to do something a little bit different. There is, thanks to Gerald, he brought this along tonight. There is a type of adapter you can purchase. Companies like Meade make it, and various other companies make them as well. This looks a lot like the T adapter I was just showing you a few minutes ago. But what's different about it is that you can put an eyepiece in it. And it allows you to do something called afocal astrophotography. And that means light is going to come in from the telescope. And rather than going straight to the camera, it's going to go through an eyepiece first, get magnified, and then hit the camera sensor. So what that allows you to do is take individual shots of deep sky objects, if you can keep the shutter open long enough that it doesn't start to streak. If you have a guided mount, obviously you can keep it open as long as you want. And it also allows you to take video, which I'm going to talk about in a sec here. So I'm going to go back to my screen share. So this is a shot taken with the Zenith Star and my DSLR and the T adapter. I took this out here at the deck at Chabot a couple of years ago. And this was taken just 200th of a second, ISO 400, like I said. And it was a very nice, steady, clear night. And I've got some very nice high resolution images of the moon that I took that night. This one was one of my favorites. I had to throw this in just because it was a great experience. This was not using my Zenith Star or any of the scopes here at Chabot. This was using the 60-inch telescope at Mount Wilson. And when we were looking through that telescope, it felt like, I mean, to use that telescope to look at the moon, there's a certain ridiculous aspect of that to begin with. But it was almost like landing on the moon, and all of us were lined up with our cameras to try to take shots of a very, very bright moon through a very large telescope. And that was the result. I wish it was sharper. It's really not, you know, that great a shot, but you could sure see a lot of magnification on those craters. Another great use for that kind of setup, having a camera, DSLR, directly attached to a telescope, is for daytime solar photography. This is using that zenith star scope with a solar filter, just a white light solar filter, nothing special, just using a Botter, essentially a lens cover that allows only a fraction of the sunlight to come through the telescope. And I got to give you a warning: whenever you are shooting the sun, you must have some sort of filter in between the lenses of the telescope and the sun, right? There has to be something cutting that energy down to a fraction of what it would be otherwise. If you don't do that, your camera will catch on fire, and possibly your eyeball as well. So definitely make sure you have thought about solar filters before you start thinking about photographing the sun. So this is using a very inexpensive solar filter. In fact, I made it myself. I got a piece of the solar film and built a little cap for the telescope that held that filter. And this is a shot of the transit of Venus taken from Mount Diablo on a slightly cloudy day. And you can see that Venus's shadow is in the upper right and several sunspots below it. And again, we're taking pictures of the sun. It's pretty bright, and you don't need to do anything special. All I needed was a tripod, figure out the best exposure after experimenting for a few minutes, and shoot away as the transit proceeded. This is some shots of the annular solar eclipse from, I want to say, 2014, 15? I don't remember. This was taken up by Hat Creek in California. And again, this was using, because it's an annular eclipse, at no point was I able to remove the filter from the camera. It's not like a total solar eclipse where once the moon covers the entire sun, you're able to remove the filters and shoot the corona. You never get to see that with an annular. Let me talk a little bit about software that you can use too. If you feel like controlling the camera with software on your laptop rather than relying on the screen on the back of the camera, if you own either a Canon camera or a Nikon camera, you will find several software products that will work really well with those. This particular product, Backyard EOS, is for the Canon camera, and it controls every aspect of the camera, including taking video. And it will also store the image on the laptop, so it won't fill up the chip on the camera. So if you only have an 8 gigabyte chip and you're taking lots of photos or taking long photos and storing them as raw images, and you're worried about running out of space, if you use something like Backyard EOS with a USB cable, rather than it being stored on the camera, it will store it right onto the hard drive of your laptop. So let's talk briefly about total eclipses of the sun. Now's a good time to think about that because we got another one coming up in a few years. So now's the time to start practicing, because if you get good at practicing now, you'll know what to do when the actual eclipse arrives. That is probably the most spectacular fast frame astrophoto shot you can take, is of a total eclipse. The challenge is dealing with the variable exposure. The nature of the light during an eclipse changes dramatically. it changes from being blindingly bright to extremely subtle and dim. And you need to be taking lots of different exposures while the event is happening in order to capture all aspects of the eclipse. And again, there's software to the rescue. There's a great piece of software called Eclipse Orchestrator that allows you to set up all of your shots in advance. And I'll show you what a screenshot of that looks like in a minute. So these were some shots taken of the most recent total eclipse in North America. Many of you were along the path of totality watching it, and a number of you were also taking photographs. So you could see that, you know, I was lucky. I caught the right exposure at the right moment, got the flares in the around the upper right side of the sun. Here's a shot of the corona. Again, this was taken with the Zenith Star Scope and the DSLR camera that I showed you. And Bailey's beads. And this is what Eclipse Orchestrator looks like. It kind of looks like a horrible looking spreadsheet. And that's pretty much what it is. And what it does is it lets you identify the camera. It allows you to identify what exposure is going to be used at exactly what time. There's a countdown clock here. And what ISO you want to set the camera to. And whether you want to store it as a RAW or a JPEG. And basically it controls all the important aspects of the shot, and will do so automatically. All you really have to do is get the camera lined up before the eclipse starts, get it as focused as well as you can, make sure that the clock on the computer is exactly right using like a GPS or even just setting it with your cell phone, and hit go, walk away, enjoy the eclipse, take the filter off when it's time to take the filter off, put it back on when it's time to put the filter back on, and then hope for the best that the camera did its thing properly and captured the images. So it's a wonderful tool. Just Google Eclipse Orchestrator. It's a free download. And there are several examples on the internet on how to get it set up and several tutorials. Also, if you get in touch with me at some point after this presentation, I can point you in the right direction for this. This is a must-have tool for eclipse photography. I did mention video, and video is a special case for DSLR astrophotography, and it's used for photographing planetary targets, Jupiter, Mars, Saturn, Venus, and you acquire the images with a DSLR or with a video camera attached to the telescope. You could use either prime focus, like I showed you with just the MTT adapter, or eyepiece projection, which is the afocal method that I showed you using this gadget with the eyepiece in it. And then you take apart the video into individual frames, and then you take those individual frames and you stack them using astrophotography stacking software. The one I use is called AutoStackert. It's a German stacking program, and it's spelled funny. It's AutoStackert, also a free download. And then you could bring out detail with other types of software like Photoshop or Registax or any other piece of astrophotography software that suits your fancy. This is an example of using eyepiece projection on a C14 telescope with a simple DSLR camera with about 2 minutes of video. I personally like the one on the left a little bit better because it's sharper. But you see an awful lot of detail on Mars in both of these shots. And that's what happens. A couple of minutes of video, take apart the video, stack them up, and do a little bit of processing, and you get a pretty nice shot. That's a not so nice shot of Jupiter, but it gives you the idea that Jupiter's a hard one to do. Jupiter spins so fast that you can only take about 2 minutes. The moment you go beyond 2 minutes, everything starts to blur because the rotation rate of the planet is so fast. And this is one of those images where you say, why do I even bother? This is Damian Peach and his photos of Mars. He and Christopher Go are the two best planetary video astrophotographers alive today. They travel all over the world to locations that are particularly well suited to this type of astrophotography, and they do phenomenal work, meticulous work, to get these very high resolution images that are better than many space telescope images that I've seen. Here's another one. That's a lot better than my Jupiter shot. This one is also by Damian Peach. Yeah, this is Gerald just said this makes you want to give up astrophotography. But these guys are amazing. If you haven't seen any of their work, just search Christopher Go, and that's G-O, or Damian Peach, Peach spelled like the fruit. And then finally, deep sky astrophotography, or how to always be poor. Now, deep sky astrophotography is the holy grail of astrophotography, and it's the holy grail of astrophotography because in order to afford it, you have to find the holy grail. And it's all about the mount, and you get the mount right, and then you worry about the telescope, and you'll need a camera, and then you'll probably get another one shortly thereafter, and probably another one after that. And don't forget the guide scope, the software, the motorized focuser, the filters, the field espresso maker. A psychologist comes in handy, computers, hand warmers, illuminated reticle eyepieces, batteries, more batteries, car batteries, boat batteries, battery charger, USB hubs, USB cables. And that's just part of it. And I'll tell you, it's endless amount of fun and frustration at the same time. There's a real zen to doing this. And I've mentioned guiding several times. So what is guiding? Well, this is a picture of a guide camera and a guide camera attached to a telescope. The guide camera sits on top of the telescope. Sometimes they're integrated into the main camera, and that's called an off-axis guider. But for the moment, we'll talk about what many people jump into, especially when they get started, is they mount a small telescope on top of their main telescope, attach the guide camera, and that guide camera then connects to a piece of software that looks for a star in the field of view and sends corrective pulses to the mount to keep the mount pointed at the target object that you're photographing. So it's constantly taking a photo every second or two, saying, oh, I got to nudge this a little bit south. Now I got to nudge it a little bit east. Now I got to nudge it a little bit south again. And it tries to keep the guide star centered, so whatever you're photographing does not get blurred and that the stars around it do not become elongated. It's basically doing what the film astronomer I alluded to at the beginning of this presentation used to spend all night doing with his illuminated reticle. But here you get to let the mount and the guide camera do it by itself, and you can kind of walk away and do something else or chat with your friends while the mount is guiding. So this is what guide scope software looks like. This is a piece of software called PhD2, and it's a remarkable piece of software. Again, it is free. A lot of really great astronomy software is either open source or free for download. People do it because they love doing it. They write it because they love writing it. And they take donations, of course. But some of the best software products I've ever worked with are astronomy products that are free of charge. And this is one of them. And you can see that the graph on the lower part of this image is showing the tracking of the right ascension and declination. And there's very, very little deviation from the center, which means that this is a very well guided telescope. And you could see these little blue bars, if you look closely, some pointing up and some pointing down. Those are representative of the correction pulses that the software is sending to the mount periodically as the star that it's tracking, which is right here in the middle of the crosshairs, deviates from the intersection of those two lines. So once you get the scope guiding, you start shooting your target. You're going to determine your exposure time. If you're using a monochrome camera, you figure out how much time you want to shoot black and white. And then if you're going to use red, green, and blue filters to get the color, how much time you want to spend doing that. You basically put together an exposure plan and then capture all of those images. Typically you take 5 to 10 minute shots, gather anywhere from 20 to 100 of those. And then once observing season is over and it starts to rain again, then you spend your time with the processing software creating your final images. The idea is that you take all of these short images and you stack them. And when you stack the images, it's not an additive process. You're not saying, okay, I've got this dim image of a galaxy and now I'm going to make it brighter because I'm adding those pixels together. That's not what you're doing. What you're actually doing is averaging the image as you stack it and increasing the signal to noise ratio, which is beating down the noise and making your blacks blacker and your whites whiter and teasing out the details from the natural noise that's in the camera or from the background light pollution that's in your frame. So this is a tool that I often use called Astrophotography tool, and you can see that there's a particular image that's being taken of what looks like the Pleiades. And this is taken actually with a one-shot camera, one-shot color camera. And on the right-hand side, you can see that you could plan your exposures. It's going to take a 300-second exposure, and then it was going to be followed by 180 seconds and a 90-second and 30-second. I wasn't the photographer on this. I'm not sure what he was trying to achieve. It was probably bracketing, taking different exposures with different well, I would think it would be with different ISOs, but that doesn't look like the case either. So I'm not entirely sure what he was doing there. Probably just to see how different exposures came out and see which ones had the least amount of noise and was most suitable to final processing. Maybe he didn't trust his mount. I'm going to skip that. So here's a 5-minute shot, and it doesn't look like much. It's one frame, and all you see are a few stars in there. It's not that exciting. So why was I spending the time? Well, if I stretch that image, meaning I say ignore everything on the, really ignore the white side of the curve, the light curve, and tell it that the dark side of the light curve should be the part that I concentrate on. That didn't come out well. Basically, you've got a linear progression of on a digital photograph of black to white. And that would be what you normally see is a certain amount of stuff is white and a certain amount of stuff is black. In an astrophotograph, most of what you want is way over on the black side because it's so darn dim, it's barely detectable. So you need to change the light curve in such a way that it exaggerates the data that's on the black side of the curve. And it's called stretching the image. And so if we stretch the image, a galaxy pops out. And it's a very dim galaxy. This is actually like a magnitude 9, magnitude 10 galaxy. And you could see that there's all this gray around it. Well, that's all noise from background noise from the camera. The stars look pretty good. They're pretty round. And you can see that, hey, maybe there's some decent detail there. So take about 30 or 40 of those. And before you process it, you take what are called dark images. And darks are taken with the lens cap on the camera. And you take a whole bunch of those in order to figure out what part of the image is real and what part of it is hot pixels and what part of it is dark noise generated by the camera naturally without any light coming into it. And all of that stuff has to be subtracted out. Then there's something called flats. Now, flats are a way to record the optical error of the telescope system. And you see all those little circles all over the place. Those are dust donuts. Each one of those little circles is a speck of dust somewhere on my optical system. And there's an awful lot of it. Most of these are probably on the filters in front of the camera. There's some big dust donuts behind it that are probably on my focal reducer. And there's also, notice these corners, these dark corners, they're terrible. That's caused by what's called vignetting. And the light being collected in the corners is much lower than the light being collected in the center. And all of that has to be calibrated out of the actual images that I want to process. And we do that by what's called dividing the flat out of the data images. So when we're done stacking, aligning, and processing the image, you get something like this. So this, a bunch of these end up becoming something like that. And that's pretty decent. And here's another example. This is the fireworks galaxy. And this is the first astrophotograph I did that was worth showing anybody. And that's the Crescent Nebula in Cygnus. And of course, the Trifid Nebula. So start saving pennies. And stop the screen sharing. Those deep sky photographs, by the way, this is what a CCD camera looks like. And the red box here is the actual camera. The sensor is inside of it. There's a place for airflow, the air circulation. There's a fan in here to blow the hot air out of the camera as the Peltier cooler cools the sensor. This funny round thing contains filters. Red, green, blue filter, ultraviolet filter that blocks the ultraviolet light. And I've got what are called narrowband filters as well, which I'm not going to talk about. And all of this attaches directly to the telescope. And the ideal circumstance for taking these types of photographs is to set up the telescope in a place where you won't have to move it for a couple of days. So you can get 2 or 3 nights of images and get a lot of data to stack up and process. So anyway, that's the overview of this crazy hobby. And I hope, let me put this down. I hope that some of you will find a niche in here to experiment just with stuff you've got laying around at home. Or if you feel like you want to invest in this hobby and spend time in one particular area, I hope you have an idea now on what's involved. It's a vast topic. Any one of those slides, I probably could have gone on for 2 hours on its own. So I tried to compress a lot of information into a very short period of time. I'll take questions from the Facebook page.
I'm going to ask about Comet Swan. It's still visible in the very early morning hours in the eastern sky, just above the horizon.
Okay, Comet Swan. Somebody asked about Comet Swan. Very early in the morning, like 2 in the morning, 3 in the morning. Yeah, 3 in the morning in the southern horizon. If you are east or south or southeast?
almost straight.
Oh, it's straight east. My mistake. Go to skyandtelescope.com and they have some very good star maps of exactly where it is. It's not, terribly bright, so you need to be able to point your telescope according to stars that are in the immediate vicinity. Once you've got it in the field of view, you should be able to see it. But you're going to need to do this at like 3 in the morning, pointed at the eastern horizon. And that might be tough depending on where you live. Any other questions? What else have we got? Sorry, bear with me. I got to scroll to the bottom. Oh, excellent. Somebody was mentioning that they wanted to take pics of the moon with a Leica camera. Beautiful camera. Leicas are fantastic cameras. They've always been among my favorite, and I've never owned one myself, but I've always enjoyed using them when I've had the chance. Yeah, you're going to have to, take some bracketed shots. You're going to have to decide which ISO and exposure works best. In my particular case, I usually did, 200th of a second, 400 ISO, but you'll experiment. You'll find what does not wash out the image, because you really don't. That's always the main concern with shooting the moon, is that you end up washing out the image. And it's better to be a little too dim than to have saturated the pixels. Long lens probably costs as much as a small telescope. You bet. Those long lenses for cameras, they cost more than a lot of telescopes. And I think the telescope method is the better way to go than the high-end camera manufacturer lenses. Those lenses are really meant to be used terrestrially. That's what they're designed for. So there's a lot of glass and mechanics in there related to terrestrial photography, whereas a telescope has a simpler system of lenses, and it will allow more light through, and there'll be less internal reflection. So it's generally a better way to go. What else have we got? Oh. Yeah, very, very good point. Whenever it's tough with a CCD or CMOS camera to test during the day, because they're so sensitive. All you get is a white screen. You almost have to use those at night. But for DSLR through a telescope, yeah, absolutely. You want to test as much as possible during the day. For eclipse photography, you want to get your solar filter on the telescope and just take shots of the sun without the eclipse, and to make sure you're able to shoot the sun, shoot the moon, take lunar photographs during the day, understand the difference of the brightness of the sky between the day and the night, so you're comfortable with the variance in exposure times. You almost want that to be second nature through practice. I do want to mention somebody asked about applications for the phone. I use a product called Pro Camera for Android, and it allows you to do all of the adjustments that I discussed. You can turn on raw image storage. You can set a timer. You could turn off HDR. You could set the exposure time to the maximum that the camera will allow. You can adjust the ISO. You can adjust the focus. It displays the composition grid that I talked about, and it has various other effects and settings as well. And it's free. It's called Pro Camera for Android. I highly recommend it. I've been really enjoying using it, and haven't quite replaced the regular camera application that came with Android, but this one is starting to really grow on me. My understanding, I'm not an iPhone user. I don't have an iPhone, but I understand that many of these features are already built into the iPhone, and you guys can correct me if I'm wrong. I don't know if that's true or not. Let's see.
this gives a link to another Google phone, Android phone app.
Which one?
Phone,
What's it called?
doesn't give a name, Deep Sky Camera.
Okay, so somebody mentioned another app called Deep Sky Camera. I'll check that out as well. It's always great to have other recommendations. I did not do an exhaustive search, that's for sure. Also, Android has released very recently for Android 10 an extension to some of the manufacturers' cameras. Certainly, the Google camera has it. Astrophotography mode, which is really not astrophotography mode. It's more like dark lighting mode, or a dim lighting mode. So it allows you to take nightscapes and various low light photographs with greater ease than the built-in application normally would. But it doesn't really seem to be suitable for astrophotography, even though they claim it is. I'm skeptical. Let's see what else we got.
How does the guide work when you want to track stars as a movie?
Okay, how does guiding work?
Yeah, she says, how does the guide work when you want to track the stars as they move? Is it motorized?
Okay, so the guide camera that I showed you is controlling whatever your camera is mounted to. So if you have a high-end mount that has a computer interface, then the guide camera is deciding that the mount needs to be speeded up or slowed down or nudged in a particular direction. And it will tell the mount, hey, move a little bit this way or move a little bit that way. If you have something like a Vixen POLARIE, which was kind of the inexpensive motorized mount for cameras that I showed earlier in the presentation, there is no guiding option. All you can do is rely on the motor that's built in. Basically, it's a clock motor. It presumes that in 24 hours, it's going to do it full rotation, and it tries to do it as smoothly and accurately as possible. In the end, though, the best you can get is a minute or two on your exposures. You're not going to be able to do 5 or 10 minute exposures with that. And all right, I'll tell you what I do. I'm going to close the presentation, and I'll stay on the chat alongside the video for a few extra minutes. If you guys want to ask me any more questions, I'll do my best to answer them.
Can you show us the logo for the ProCam?
I'm not sure what the ProCam is. Yeah, sorry, I don't know what that is. So.
Says ProCamera is also available on the iPhone.
Oh, got it. Gotcha. All right, maybe that's what they were talking about. So yeah, Leslie mentioned that ProCamera app is also available for the iPhone. That's excellent. I think that's one of the better apps. So that I evaluated about 6 of them, and uninstalled all of them except for that one. And that one's a keeper for me. Okay. Good night, everybody. Thanks for listening. I hope you got something out of it, and enjoy the rest of your weekend. And we'll see you next time.